Let's look at a system of observers. Our primary observer, an aggregation of nuclei particles, believes itself to be at rest. A small distance away is an electron, which we will call our co-observer. This electron is speeding past the nucleus. Let's contemplate the mechanics that arise between nuclei and electrons existing within a uniform scalar field. We will construct the relationships that describe matter's continual dance as it attempts to reconstruct its observed reality as it is continually fractured in the field. Both particles of matter and bosons occupy a given volume of Euclidean space. Similar to the field relationships we have already constructed, we will build in the three-dimensional realm of Euclidean space. Within Euclidean space, let's imagine a nucleus composed of an aggregation of protons and neutrons. Traveling past this nucleus is the fast-moving particle called an electron. Let's state that the system observes what it considers reality at this moment. Immediately after this instant, the system observes the expansion created by the scalar field. Let's establish that the aggregation of particles forming the nucleus functions as the primary observer. The electron speeding past we will establish as the co-observer. Like before, we can readily swap the primary observer and co-observer roles. From either party's perspective, we can observe the reality constructed between the nuclei and the electron. For what I believe is a more precise illustration of the mechanics, let's call the nuclei our primary observer. At some instant, the primary observer observed the electron. The primary observer observes the state of the electron. The primary observer notes the mass and incredibly fast relative motion of the moving electron. The primary observer noted the state of the electron to describe reality. Following the universe's fundamental laws, we know the primary observer's reality must be conserved. Instantly, the system observes the scalar field. The nucleus, our primary observer, now observes the electron to be in an unexplainable energized state. The electron is initially located at an extremely small distance from the nucleus. This distance between observers, determining the velocity of the field, means that the primary observer observes only a slight momentum change in the electron. Even though the momentum change produced by the field is extremely small, the electron is initially moving at an extremely fast speed. In fact, the electron is initially moving at about 2200 km per second relative to the stationary nucleus. Taking the speed of the electron into account, the influence of the field, albeit extremely small, would be adding to the velocity of an already fast-moving object. Similar to our gravitational regime, we must consult the Lorentz transformation to describe how the primary observer observes the effects of the scalar field on the electron. Given the initial speed of the electron, very little of the momentum gained by the electron is observed as a change in velocity. Instead, the primary observer observes an increase in the mass of the electron. The primary observer's initial reality must be conserved. This means that the nucleus, at some point in the future, as a primary observer, must re-observe the electron to exist at the same state the nucleus witnessed before it observed the field. What happens if we try to follow the electron's original trajectory? We can see that the electron would move further and further from the primary observer. This would not be good for our primary observer. The already energized electron would be moving further out into the field, and the primary observer would observe the electron to be continuously increasing in mass as the strength of the field increases. The electron cannot be allowed to leave the immediate vicinity of the primary observer. If the electron escapes into the field, the primary observer will witness the electron, initially observed to be a tiny particle, to be continuously and unexplainably gaining mass. This unstoppable and irreversible process would not be good by any means for the universe's fundamental laws of conservation. Obviously, since we don't see electrons the size of school buses zooming around us in everyday life, there must be a process that can maintain the electron's proximity to the nucleus and return the particle to its initially observed ground state. Only one conceivable process will conserve the primary observer's initially observed reality. Similar to the field cycles we have already constructed, the primary observer's relationships dictates its observation of its surroundings. This means that the primary observer can amend its state during field cycles to change its observed state of another body. How can the primary observer witness the electron completely reconstructing the nucleus's initially observed reality? Suppose the electron was constantly spending its dilated mass from the field to accelerate itself toward the primary observer. In that case, the primary observer might observe the electron constantly adjusting its velocity and orbiting the proton. Eventually, the primary observer observes the orbiting electron to have lost all of its dilated mass. The state of reality that the nucleus initially observed has been reconstructed at this instant. The electron must repeat the process. Over and over again, the field fractures observed reality and the primary observer reconstructs it. But isn't it the electron undergoing the process? How does the primary observer reconstruct reality? Despite observing the entirety of matter within its observable sphere, the primary observer cannot view its own glance. The primary observer observes its surroundings but only understands its existence relative to the other bodies. Therefore, the field modifies the state of all matter surrounding the primary observers. To mediate a fracturing of reality, the primary observer must adjust its own state. Changes are made by the primary observer to re-establish its observed relative relationship to its surroundings. So rather than consider the electron undergoing the process, we can describe a process for the primary observer to undergo that will allow it to re-observe the electron in its initial state. Rather than perceiving the electron spending its dilated mass to accelerate toward the primary observer, we can consider the primary observer accelerating toward the electron. As the primary observer accelerates, it believes the electron to be losing its dilation. Because the primary observer cannot observe itself, accelerating toward the electron does not violate the laws of conservation. The only important thing is that the state of its observed surroundings abides by the laws of conservation. By deciding to accelerate toward the electron, the primary observer reconstructs the surrounding reality it initially observed. In the end, the primary observer changes its state to re-establish the state of its surroundings. Despite changing its internal state, which it cannot quantify, the primary observer finds itself observing conservation in its surrounding reality. Given the unique mechanics of processes of matter in the scalar field, we can see that the combination of the two overlaid observations ensures that the individual parties can only observe the field's fracturing of reality within the system. To an external observer, the reality of the combined system appears to remain constant despite it being continuously internally fractured. What we humans observe to be reality is actually a simultaneous combination of both particles' observations.